MPLS, or multiple protocol label switching, is a fairly new protocol in the wide area network or the WAN environment. It's a scalable and protocol independent. The data packets are assigned labels, and packet forwarding is dependent on the label and not the content of the packet, which allows it to permit traffic engineering. It dispenses of any cell switching and signaling protocols, baggage of ATM. It provides quality of service and defense against network attacks, and it operates at layer 2 and layer 3. In broadband, WiMAX allow implementation of wireless metropolitan area networks with download speeds up to 100 megabits. We have improved access when a base station and a user are not in line of sight. 50 kilometers approximately from the tower, and also security is based on AES and EAP. When we look at wireless optics, two laser transceivers communicate at speeds comparable to SYNET, which is synchronous optical networking. Wireless optics transmissions are very hard to intercept. However, it can be unreliable in inclement weather, such as snow, sandstorms, rain, as well as fog. We have a global area network, which is part of the internet, intranet and extranet, which is granting access to external organizations, and a broadband global area network, also known as BGAN. The TCP/IP is the network layer, and it's the de facto standard for communication. However, we need to provide private communication service over a public network, and then we have the Internet Protocol, which is responsible for sending packets over that network. It is unreliable. It will subdivide the packets, and it's got two structures. The old structure, which is IP version 4 address structures, which we saw, and then IP version 6 to address some of IP version 4 shortcomings. The protocol structure address is class A, B, C, D, and E. We've seen that before of all the classes. However, this table identifies the number of octets for the network and the maximum number of hosts in a network. Normally, you'll have class C in your network, which has 254 addresses, where 0 and 255 is removed because 0 is a broadcast and 255 is the network. And up to class A can have 16 million plus in a network, but however, you won't do that, of course. At the transport layer, we have TCP and UDP, where TCP, which is Transmission Control Protocol, is a reliable data transmission, connection orientated, so there's a handshake and an overhead, and maintains status and state, known as stateful. UDP, or User Datagram Protocol, provides best effort transmission. It's connectionless without flow control, does not maintain status and state, so it's stateless, and does not offer any error correction nor retransmission. So TCP, in a little bit of detail, is a connection-oriented transmission that maintains status and state information of each user data stream flowing into and out of the TCP module. It's connection-oriented, reliable stream. Packets are resent if a packet's unrecognizable or is not received, and connection-oriented protocols are sometimes described as stateful because they keep track of a conversation. UDP is a connectionless transmission that do not require the receiver to acknowledge the receipt of a packet. Instead, the sending device assumes that the packet has arrived. Much faster due to the fact there's less overhead than TCP. It's less reliable because UDP does not offer error correction, retransmission, or protection from lost, duplicated, or reordered packets. Connectionless protocols are usually described as stateless because they have each end has no protocol-defined way to remember where they are in the conversation of message exchanges. Now, there's a couple of examples here from TCP and UDP. The only thing I can actually recommend you here, you need to actually look at your Windows or your Unix workstation and look at the services file and see what port numbers these are normally running at. Question I was posed to understand, do we need to know the port numbers? And I think it's very easy to remember some of the most basic port numbers because, for example, if you look at SSL there, which is 443 normally, it's very important, as some of the questions may come up on this. The interesting thing between TCP and UDP is that DNS sits both at the TCP and at the UDP level. At the TCP level, it's for zone transfer, and at the UDP level, it is DNS queries. Now, when we look at the session layer, what happens at the session layer? The session layer provides services to establish a session connection between two representation entities and supports orderly data exchange interaction and to release the connection in an orderly manner. This means to me the session is created, managed, and destroyed. We can have different connections such as duplex and half duplex mode. It is session connection synchronization. Examples of session layer protocols include things like NFS, which is network file system, RPC, remote procedure call, NetBIOS is network basic input output system, and SQL, which is structured query language. At the presentation layer ensures that the communication passing through are in the appropriate form for the recipient. Programs in the presentation layer address three aspects of presentation. Syntactical compatibility, which means data encoding and conversion sent from the application layer to one system will be readable by the application layer of the other system. Encapsulation of data into messages or envelopes for transmission through the network, for example, EBCDIC to ASCII. An example of data formats includes ASCII, the American Standard Code for Information Interchange, EBCDIC, Extended Binary Coded Decimal Interchange Code, Tagged Information File Format, TIFF, Joint Photographic Expert Group, JPEG, and Motion Picture Expert Group, MPEG. Then at the transport layer, TLS, Transport Layer Security, which is a successor of SSL. The function of TLS is mutual authentication, asymmetric cryptography for authentication and key exchange, symmetric encryption for confidentiality, message authentication codes for integrity, and also we've seen the development for wireless transport layer security, which is part of the Wireless Application Protocol, WAP. Now, directory services include things like DNS, Domain Name Services, LDAP, Lightweight Directory Access Protocol, which is X500, Network Basic Input-Output Systems, NetBIOS, Network Information Service, NIS or NIS Plus, which is originally the Yellow Pages from Sun Microsystems. We've got Banyan Mines and also the Windows Registry, which is the browser. Now, access services include things like the Common Internet File System, CIFS, or Server Message Block, SMB, which is the shares in Windows. We have NFS, which is a Network File System, Secure NFS, Remote File System, RFS, WebDAV for Web Development, Network Neighborhood. We've seen that in IP version 6, DCE and RPC, and also AppleTalk. At the final layer, which is the application layer, we have where it provides services for application program that ensures that communication is possible. Communication is the crux here, the key word. It makes sure that the necessary communication resources exist, ensures agreement at both ends about error recovery procedures, data integrity, and privacy. It determines the protocol and data syntax rules at the application level. And examples of application services are things like FTP, File Transfer Protocol, Trivial File Transfer Protocol, which is TFTP, Simple Manual Transfer Protocol, which is SMTP, Simple Network Management Protocol, SNMP, Telnet, Hypertext Transfer Protocol, HTTP. Then we have ports and protocols, and there are 35,535 TCP and UDP ports because 0 does not count. And as said, you can look at under ETC services in Unix, and then also your System32 directory drivers, ETC, and the file services, which you can browse through and actually look at the most common relationship between the port number and the service name. Now, also during a data exchange in the World Wide Web, there are a few protocols to think about. We've got TFTP, Trivial File Transfer Protocol. We've got FTP, which is sitting at port 21 and 22, one for data and one for control. Hypertext Transfer Protocol, HTTP, HTTP over TLS or SSL, HTTPS. Secure Hypertext Transfer Protocol, which is SHTTP. Passive and active content such as HTML, especially version 5, ActiveX, Java and JavaScript, peer-to-peer applications, and protocols. Then message services, we have instance messaging, which is a huge risk in networks. We could have asynchronous messaging, such as the Post Office Protocol, POP, Internet Message Access Protocol, IMAP, Network News Transfer Protocol, NNTP, and the risks include things like open mail relay service, email spoofing, spam, and then spam over instant messaging. Administration services of network devices include things like Simple Network Management Protocol, SNMP, which is sitting at UDP 161 and 162, 161 for the control of and 162 for trap generation, UDP. There's a community string, which is known in default, which may have a risk in your environment, and if it's not known, you can do a possible brute force attack using products like SolarWinds. There's remote network monitoring, RMON, and also Windows Management Instrumentation, which is WMI, which contains a language called WMI Query Language, WQL. The remote authentication dial-in user services known as Radius has got a network access server that sends authentication requests to a centralized authentication server. Now, Radius was developed by an organization called Livingston for their devices, their switches and routers. However, it has been opened up, and actually a lot of application and devices are using it, especially if you actually work with remote access services, Windows, you'll see that Radius is integral. Other issues for remote access services include TCP IP terminal emulation protocol, Telnet, or R commands such as R login, remote shell, remote copy, remote execute. However, R commands are dangerous as the password is in clear text. We have X Windows system called X11, VNC, which is virtual networking computing. However, with WinVNC, the password is in the registry with a known DES key, high risk. RDP, Remote Data Protocol, also known as Terminal Services, with TCP 3389. Information services include things like the finger, TCP 79, and you can figure at the IP address. However, at the Sun Solaris, you can actually try the following command to see if the patches have been applied. Finger 234, 234, and 123 4 times at the IP address. Network Time Protocol, it will give you information about the time stamp, but nothing about the time zone, and the main time server at ntp.org. An audit should include to check for all unneeded services. Now, voice over IP is a huge issue purely because it's an IP-based, which can be intercepted and have the same risk associated with normal networking. Protocols include H323, we've got MGCP, which is Media Gateway Control Protocol, Session Initiation Protocol, SIP, widely used, Session Description Protocol, SDP, we've got Inter-Asterisk Exchange, which is an open source PBX, with it being replaced currently for another protocol. We've got Jingle XMPP, voice over IP extensions, some proprietary application and services, and with the Skype protocol being bought over by Microsoft, getting a lot of traction. There are issues in the IP telephony, such as similar to any interconnected device. Firewall and routing can be a problem. Caller ID cannot be spoofed because there is an act called Truth in Caller ID Act of 2009. IP telephony vulnerabilities include sniffing using Wireshark. Wireshark can actually sniff SIP. IP-based issues and also user authentication and credential compromises do exist. As a review here, the OSI layer has the application layer here. It's a summary. Let's look at some applications such as FTP, TFTP, SNMP, SMTP, Telnet, and HTTP. At the presentation layer, we've got ASCII, EBCDIC, TIFF, JPEG, MPEG, and also MIDI music. At the session layer, we've got TCP such as SQL, NetBIOS, UDP such as NFS and RPC. At the transport layer, we've got TCP, UDP, SSL, and SPX. At the network layer, IP, IPX, addressing, routing, broadcasting methods such as ICMP and IGMP. At the data link layer, we've got LAN and WAN. And at the physical layer, we've got network cables, infrared, optical fiber, etc. Then network devices, if we can quickly look at that, we've got things like bridges, which is a network device that connects multiple network segments, which sits at layer 1. Hubs, at layer 1, there's no management of traffic and no security for delivery. A switch at layer 2 and 3, and a router at layer 3. Now also layer 2, maybe we need switching. Layer 3 is routing, which is awareness of IP multicasting through IGMP snooping. Layer 4 is network address translation and load distribution. And layer 7 is load distribution via URL, such as web caching and content delivery of the network, and usually vendor dependent. Now, from a security controls and countermeasures, we need to look at each layer that forms part of the defense in-depth approach and is a perimeter to secure. Exposure in one may act as a springboard to the next level. Layers selected we can look at quickly is a couple of layers such as physical. Let's look at the data, IP network, transport, and the application layer. Some controls we can look at is routers, switches, special encryption devices. We've got firewalls at the service level and application level. There's intrusion detection systems, improvement prevention, and also at the kernel protection layer at the operating system at ring 0, which is the hardware abstraction layer. Now, what we can do about the physical layer, we can look at cables and we can look at LAN and WAN. There's communication. We've got radio frequency. We've got for a LAN, also for WAN, and then line of sight, infrared, and also laser. What can we do to protect these? From a physical point of view, we can actually put the cables in casings. We can put them in vacuum tubes or air-walled, concrete, steel pipes, conduit, and also physical access control cabinets. In the radio frequency, we may have a Faraday cage, shielded cable, Tempest certified rooms and buildings. Now, Tempest is a technology that is there to make sure that emissions are protected and controlled within an environment and nobody can sniff your emissions. Light, line of sight, and triple alarms. When we look at switches, we can disable ports not used. We can lock a port to a MAC address, enable SNMP trap generation on illegal MAC addresses, disable that port on an unauthorized MAC, and then administrator intervention for enablement. We can designate a specific remote IP for management, also remote IP for monitoring, and ensure that these anomalies take place has to be within the help desk and incident management processes. Network equipment, we have to enable passwords on routers and switches. We can change the default passwords. For example, 3Com has got 3 users, admin, manager, and security with the same password as the name. We can use centralized access management such as Radius or TACACS and TACACS Plus. We saw that in the previous domain access control. We can enable logging using syslog, simple network management protocol, and also remote monitoring. Compliance and warding banners. At the next section, we've seen password authentication protocol RFC 1334, which uses authentication process, which is plain text, and is sent over the established link, high risk. We have a challenge handshake authentication protocol, CHAP, which is RFC 1994, and it replaces 1334. And we saw that earlier, that CHAP requires a secret key to be available in plain text form, but the secret key is never sent over the link. It uses the 3-way handshake. At the data link layer protection, we can use PPTP, point-to-point tunneling protocol, which does not prescribe security. However, implementation does use various levels of authentication and encryption in the tunnel. L2TP, which we see is RFC 2661. It does not prescribe security. However, implementation does use various levels of authentication and encryption in the tunnel. IPsec, it's an RFC 4835, one of the most implemented and used open security protocols. It uses HMAC SHA-1 for integrity protection and authenticity. It uses triple DES cipher block chaining for confidentiality, and AES, which is Randall cipher block chaining for confidentiality. You can actually tunnel IPsec via L2TP, which is RFC 3193. And then on the other side, competition to IPsec is OpenVPN, which uses OpenSSL library to provide encryption of both the data and the control channels. When we look at wired for wireless access, wired equivalent privacy, WEP. WEP is an optional IEEE 802.11 encryption standard. It is implemented at the MAC sublayer. It uses RSA RC4 stream cipher with variable key sizes. Shared symmetric key 40-bit, and 104-bit is not the standard, of course, but with a 24-bit initialization vector. The security issues of the WEP is the size of the IV, only 24 bits, a shared static symmetric key 40 bits or 104 bits. Hacker can collect enough frames in the same IV and find out the symmetric key using a product such as WebCrack. Mitigation, we can do IPsec over 802.11 or 802.11.11i and IEEE 802.1x, and this is all WPA2. Now, IEEE 802.1x uses EAP extensible authentication protocol. 2.1x is an interoperability standard and not a security standard. It uses a three-way handshake in state machine mode. It has unauthorized state. After the link is established, the authenticator, the access point, sends an authentication request message to the peer. Unauthorized state, the peer sends a response with a set of values that matches the authentication mechanism of the authenticator. And then at the authorized state, the authenticator calculates the expected value and matches it against the response. For authorized state, exchange encrypted data message. And the risk is man-in-the-middle attack. Now, the IEEE 802.I standard has been ratified in 2004. It is FIPS 140-2 certified by NIST, also known as WPA or Wi-Fi Protected Access version 2. It uses IEEE 802.1x, that is EAP for authentication, uses the four-way handshake. It uses AES-based counter mode, a cipher blockchaining message authentication code protocol. We've seen ARP and RARP. Just quickly to rehash that. ARP maps the MAC address to an IP address. Reverse ARP, opposite of ARP, maps the IP address to a MAC address. Preserving the integrity of an ARP table is key to the security of switching topology. We can see CAN-enable, for example, of ARP poisoning. CAN-enable is a product at oxid.it, oxid.it, and you can download it. It is known as a password recovery toolkit. However, it's a hacking tool. Do not install on your work machine without an authentication or change control. Risk is vulnerable. The ARP table is vulnerable to denial of service attacks, DOS attacks. A hacker can easily associate an operational significant IP address to a false MAC address. Then your router begins to send packets to a non-existing interface. Man-in-the-middle attack. A hacker can exploit ARP cache poisoning to intercept network traffic between two devices in your network. Also, a MAC flooding attack is an ARP cache poisoning technique aimed at network switches. By flooding an ARP table with a ton of spoofed ARP replies, a hacker can overload the network switch and put it in hub mode. Then the hacker can packet sniff your network while the switch is in hub mode. It will fix itself later. Now, to preserve the integrity of the ARP table, we can have logical access control, such as a static ARP table. However, the problem it is not scalable, however very effective. We can enable port security using sticky MAC addresses, write the dynamically learned MAC addresses into memory, and disable all unnecessary protocol and services. From a physical access control point of view, we have to disable all interfaces not in use, enable interface only when ready to use, designate specific interfaces for management, designate specific interfaces for monitoring. At the IP network layer protection, we can have logical addresses such as IP addresses. There's some controls such as ICMP, ARP, and RARP we've seen. We can have routing such as static and dynamic. We can have routing protocols such as Internet Gateway protocols, distance vector routing, link state routing protocols, and then at the exterior gateway protocol, we can have state vector protocols. At the transport layer, we can have NAT, which is network address translation, which is a method of connecting multiple computers to the internet or any other network using one IP address. An increased use of NAT comes from several factors. We've seen that before: shortage of IP addresses, security needs, ease and flexibility of network administration. Now, RFC 1918 reserves the following IP addresses for NAT, class A, B, and C, and we have seen that before. Virtual IP addresses is a method that maps a virtual internetworking entity to many competing nodes. We can have one-to-many, used for load balancing or sharing, used limited exposure for multiple IP addresses or multiple network interfaces, one-to-many. Now, many-to-one, one network interface to many IP addresses, used for application sharing, or also dual-homed gateways. Also, at the static or versus dynamic routing, we can preserve the integrity of route table, which is key to the security of routing topology. Static routing is the most secure routing configuration. However, scalability is a major drawback. A static route table, we have no automatic updates. Dynamic routing table is scalable but needs to establish a security policy to preserve integrity of the route table. There's automatic updates. We need to set a threshold and also authenticate neighbors and peers. At the transport layer protection, we may have firewalls such as packet filtering firewalls, that is router ACLs, which we do not examine layer 4 to 7 data. Therefore, it cannot prevent application-specific attacks. A proxy firewall supports selected protocols such as DNS, Finger, FTP, etc. And for multicast protocols, PIM, ICMP, it must be tunnel through the firewall. A stateful inspection firewall is faster than proxy firewalls and more flexible because it examines TCP/IP protocols and not the content, the data. Unlike a proxy firewall, it does not rewrite every packet and it does not talk on application server's behalf. Then we have hybrid firewalls such as circuit-level proxy firewalls. The IETF created the SOX proxy protocol, which is RFC 1928 for secure communications. SOX creates a circuit between the client and the server without requiring knowledge about the internetworking services. No application-specific controls. It supports user authentication. Then an application proxy firewall is application proxy and stateful inspection. A different proxy is needed for each service. It supports user authentication for each supported service. For example, if we look at Checkpoint Firewall 1 next generation, also Microsoft ASA server, which is now known as Threat Management Gateway, TMG. Now, the most common is packet filter firewalls, which is basically a router with ACLs, such as a packet filter firewall. A firewall policy is deny by default and permit by exception. Now, it understands the data flow. For example, we've got a source, a destination, protocols, and routing methods, so the security engineers how to apply the IP filtering. It knows the specific inbound and outbound interfaces, and also we need to disable all unnecessary protocols and services. Now, proxy firewalls do not allow any direct connection between internal and external computing hosts. We are able to analyze application commands inside the payload or the datagram. It supports user-level authentications, able to keep a comprehensive log of traffic and specific user activities. Stateful inspection firewall supports all TCP/IP-based services, including UDP by some. Inspects the TCP/IP packets and keeps a track of states of each of these packets if it is a low overhead and high throughput. Allows direct TCP/IP sessions between internal computing hosts and external clients. Offers no user authentication. When we look at intrusion detection and intrusion prevention, network intrusion detection is a passive device to detect attacks and other security violations, to detect and deal with preambles to attacks, that is doorknob rattling, probing, and scanning, to document the threat to a network and improve diagnosis, recovery, and correction of unauthorized intrusions. The network intrusion prevention system is an inline device which has all the same features of a network intrusion detection system, plus interference in the internetworking behavior to prevent further damage to internetworking services. A network IDS and host IDS use knowledge-based or signature-based methodology to detect intrusions. It uses a database of known attacks and vulnerabilities called signatures, only as good as the last signature update, can be difficult to fine-tune, false positive, and unacceptable behavior. Network intrusion prevention systems use behavior-based methodology to detect and prevent intrusions. It learns normal network to host behavior, alerts when behavior deviates from the norm, such as malformed packets, abnormal network utilization, or memory usage. Network-based intrusion detection systems is a passive device, and there are two ways to set up the listening. We can have interfaces such as a network tap and VLAN port spanning on layer 2 switches. Network intrusion detection system is composed of two components, which is a preprocessor, a sensor, and event collector or analyzer. Preprocessor assembles the packets and matches them against a predefined signature database. The event collector or analyzer collects the events from all of the sensors, correlates and presents intrusion patterns. A network IPS or intrusion prevention system is an inline device which will examine network traffic and automatically block inappropriate or malicious traffic. However, it may block some normal enterprises internetworking LAN traffic, so it's best to use it in between the edge router and the external perimeter firewall. It may be abused by using it as a denial of service device. At the application layer protection, we've got SHTTP or secure HTTP, which is a protocol designed for use in conjunction with HTTP. As you can see, the RFC 2660, where SHTTP is a message-oriented secure communication protocol. HTTPS is HTTP over SSL. SSL works at the transport layer level, and HTTP message is encapsulated within the SSL. Then Secure electronic transactions. SET is a system for ensuring the security of financial transactions on the internet. It was supported initially by MasterCard, Visa, Microsoft, Netscape, and other developers. A user is given an electronic wallet or digital certificate, and transaction is conducted and verified using a combination of digital certificates and digital signature among the purchaser, the merchant, and the purchaser's bank in a way that ensures privacy and confidentiality. SET uses Netscape's SSL, Microsoft STT, and Teresa's systems SHTTP. SET uses some but not all of the aspects of PKI. Not a lot of traction was found in this. Google Wallet is a new development and needs to be considered. In servers, the protection of servers, let's look at network first. We have to be specific on service functions, limit services, minimize potential exposures, focus on a single function. For example, is it a web server? Make sure only web service is running. DNS server, email server, etc. We can install host IDs. We can enforce change control and configuration management. Install antivirus, disable all processes in server not in use, and then enforce strict access control on the network interfaces and also at the application level from the operating system.